share my screen. Okay. So, hello everybody. This talk is about a tool set for helping Linux kernel developers for understanding the rules of generic data structures, namely lists in the kernel. This is joint work with Julia Lawall from Inria, Paris. The Linux kernel has gradually become a critical software infrastructure for a wide range of devices, going from smartphones to supercomputers. This success has been underpinned by a sustained maintenance effort going on the long term and involving many contributors, some of which are newcomers. In fact, about a fourth of the commits on Linux come from developers with no previous experience. The question we are addressing today is what kind of tools can we give to maintainers to help them in their tasks, in particular to quickly understand the code involving complex data structures and to avoid some typical mistakes for using the associated APIs. We frame this question by focusing on the implementation of doubly linked lists in the Linux kernel, because this is a data structure which is used everywhere in the kernel in thousands of files, because it serves as a base for implementing more complex data structures such as trees, and because its usage is non-trivial. So here is a picture showing how doubly linked lists are implemented in the Linux kernel in a generic way. The key data structure here is the structure called list head, which only contains 2 pointers to the next and previous such structure, but no other data. So in order to build useful lists using these structures, you have to embed this data structure, which is shown in blue in the figure, in 2 different data structures. So in a first one called headdef here, it serves as a list head, pointing to the start and to the tail of the list. And it is embedded in a second data structure called headdef list here to build the list elements. And here it serves as a connector between the elements. So this generic data structure allows to implement list of any kind of elements headed in any kind of other structure. This implementation has been adopted quite successfully since its introduction in 1998 until now. Its usage has constantly increased at the point that it is now pervasive in the kernel. We can see that by counting the number of calls to 2 simple functions, list functions, inserting elements into lists. Here we assume that a list is only useful if we insert elements into it. This increasing success has been justified by some benefits of this implementation. The main benefit being that of offering a shared binary code for implementing all kinds of lists and accessible through some uniform API. This API, for instance, contains a macro called list entry for accessing the containing data structure starting from a connector. It takes the pointer to a connector, the type of the containing data structure, and the name of the field which contains the connector, and it returns a pointer to the container data structure. The API also contains the functions that we saw for adding elements into lists, which take a connector and a list head in which the connector is inserted. It also contains other functions and macros for traversing lists and so on. So beside this main advantage of a uniform API, the implementation also offers some efficient access to list elements, which is guaranteed by the cache locality, which is due to the embedding of the connector within data structures. It also offers some safety guarantees because it implements some concurrency features. And finally, the implementation provides a high degree of flexibility, which is very appreciated by advanced developers. But alongside these benefits, this implementation poses a serious challenge to maintainers, because maintainers do not see this ideal picture with the clear role of every component, but rather they see just a textual definition of data structures, sometimes containing this list head component. Furthermore, the definitions are frequently given in different files, as is the case for our example, and there is no comment relating them in any way. In fact, only a big third of the list fields have associated comments. And many of these comments do not talk about list aspects, but about concurrencies and locks, for instance. So, given these textual definitions, maintainers have to ask them two kinds of questions. The first question is, what is the role of this structure? Is it here used as a list head or as a list connector? And depending on the answer to this question, there's a question about the relationship to other structure. If this is a list head, what kind of elements can this list contain? And if this is a list element, what kind of lists can contain this element? So in order to answer these questions, maintainers have to do some manual inspection by studying how the list is really used in the code. In our example, there is a traversal of a list headed in a HitDef structure and visiting elements of kind HitDef lists. So this makes clear the relationship between this structure and this one. And also it exposes some fields of this data structure which contain the head list and which is used to step between the elements, so which connects the elements together. This interpretation of the list is confirmed here by another list operation, which inserts a structure of type HitDef list into a structure of type HitDef. The problem is that manual inspection is tedious and error-prone, because type information can be found in the usage operations, but it is scattered in different files and requires also C-type information, so it cannot be found by using grep, for instance. The solution we propose is to automate this manual inspection using type inference. And for that, we propose a small type language associating head of lists to the possible elements. We write this, that the list L may contain elements of type L1, L2, and so on, where each variable of kind L may be either a field of the data structure or a name of the variable of type list head. For example, in our case, we can compute the type that hitdef.list contains element of hitdef of kind hitdef.list.node. This exposes all the type information of the list. It says that the list is headed in a structure called hitdef, and in particular in its field called list, and it contains elements of type hitdef.list, which are chained through their field called node. To compute this type inference, we use some type inference rules associated to the different list operations. For instance, where this operator is used to traverse a list L, visiting element of kind F and stepping through field F, we can deduce that the list contains, among others, structure S, structures of kind S, linked through their field F. There is another type inference function associated to list insertion functions, and so on. Based on these type inference rules, we built a tool set called Lilliput, which has this architecture. It contains a first tool, which scans all the kernel sources to find all the list uses involving the different showing the different types which are used in this operation. This report is textual as it is human readable. It can be directly used by maintainers to ease their manual inspections, but it can also be filtered by another tool to focus on specific kinds of uses of lists. And the same report serves as a base for our type inference tool to automatically compute the type information of any list whenever there is enough information in the uses. This type report is also textual, so it can serve directly for developers and maintainers in textual form, or can be put in a visual form by another tool, which is a visualizer. We applied our tool to all the stable releases of Linux between 3.0 3.0, when lists were first introduced, to version 5.6, which was the last version when writing the paper. We can see here that the total amount of lists, the blue dots, topped to more than 10,000 lists in the last version. Out of this, the black dots represent the lists that could have been typed, that have been typed successfully by our tools, which represent around 90% of the total, depending on the version. There is also a small fraction, 6 to 10% of the list that could not be typed by our tool, either because they do not use the official API by using directly pointers, for instance, or because their usage do not reveal enough type information. And there is also 3 to 5% of the list which appear to be unused, but this is also useful information for maintainers. Let us focus now on 2 versions of the kernel and see what kind of types have been computed for the lists. We can see that about 40% of the lists have been typed as elements only, and more than that, almost 60% have been typed as list heads. So there are more list heads than list elements. This is explained by the fact that a list element typically belongs, can take part in different lists, like as shown in this picture. Actually, this graph is computed by our visualization tool, and the excerpt we're examining is centered around a central data structure to the kernel, which is a structure describing a running task. This structure contains no less than 12 list fields. The ones in blue represent list heads, and the one in black were identified as list elements only. So let us now examine 2 interesting patterns in this picture. First, there are some lists that contain themselves, such as the thread group field. So this typically corresponds to a common pattern that we call an umbrella, which is a tree of height 1, a doubly linked tree of height 1. So this type expression tells us the fact that the field is used both as a list head in a parent task and as a list connector in the list of children tasks of this task. This explains why the tree is limited to a height of 1, because the children cannot have children of their own, because the field is already used as a connector field, so it cannot be used anymore as a list head. I said that the umbrella is doubly linked because there is another field which is not of type list, which serves for children to point back to their parent. And the parent distinguishes itself by pointing to its. Note that a simpler version of umbrellas without the distinguished leader and without the backlink is used to commonly implement rings. Please refer to the paper for the details. A second pattern we want to examine is when there is a link going between 2 different fields of the same data structure, which means that this field is a list containing such fields. And this corresponds to a tree of arbitrary height. So this is this type expression expresses the fact that there are 2 different fields, one which is used as a head list for containing a list of children, and another one is used as a connector to connect the different children together. So this is how the tree can have an arbitrary height. In some cases, the tree is doubly linked, meaning that children use another field to point back to their parents. This is a case for a task structure, but has not been shown on this figure. Besides identifying common data, our tools have not been designed specially for detecting bugs, but can reveal some unusual type patterns that we call type smells, such as 2 lists containing each other, what we call the mutual pair, which in fact frequently corresponds to an error of inverting the arguments to a list add to a list insertion function. Actually, this is not an uncommon mistake because we found 11 previous patches just inverting arguments to these list insertion functions. And out of these 11 bugs, our tools could have detected 8 of the bugs because it shown this type smell of 2 mutual lists. Furthermore, by inspecting this type smell, we could identify 6 new bugs, which were confirmed in the meantime by developers. In particular, this example corresponds to a list of clocks containing clock descriptors, as is revealed by this list traversal. This interpretation is confirmed here by another list traversal. But somewhere else in the code, there is a list insertion inserting a list of clocks into a clock descriptor, while the normal is to insert the clock descriptor into the list. So here the arguments were accidentally swapped, and this explains the backlink that shows up in the figure causing the loop. In conclusion, we defined a type system associating list heads to list elements, which works for 90% of the list above, and is accompanied by a visualization tool helping to understand complex patterns involving lists. Our tools can be used to retro-document the code to fill in the missing comments, for instance, but also occasionally to find some bugs through this notion of type smells. A variation of the type inference tool could be used to enforce some type discipline if developers would agree to trade some flexibility for detecting bugs more reliably. Several generalizations are possible of our tools, such as inferring higher level types and lists, such as the umbrella and trees and rings that we talked about. It also could be generalized to study other kinds of lists that are defined in the Linux kernel, optimized, for instance, for caches or other specific needs. Or to study other data structures, such as red-black trees, which are defined in the kernel without using lists, but in a native way. Finally, it can be used in other operating systems, which are using this pattern of embedding connectors in other data structure to ensure cache locality. So this is a quite common design pattern in efficient system code. As a last word, the supplementary material at this address contains the source of our tools and allows anyone to reproduce our results. Thank you for listening, and I'm available for questions.
Okay, thank you, Nick, for the presentation. Any questions to ask Nick? Okay, I have one question.
Yes.
How to find all the type inference rules? You find several, like 40 inference rules or hundreds. I just can't remember it. So how to find all the type inference rules? It is manually or automatically extracted?
Yes, very good question, because this is the heart of the intelligence of our tool. So it is a rule-based system. Rules were found in an empiric way by studying uses and understanding uses of the list. So we started by this, we really started by doing manual inspections of different cases and understood how the usage reveal some information about types. And also find cases where the information that we found in the code was contradictory. So this improves, this augments the usefulness of this tool, because if you are doing this manual analysis, you may examine just one part of the cases, and you may think that a list has a certain type, but in fact other cases in the code can add supplementary information, which sometimes add or sometimes contradict the first information.
Okay. Thank you. I just saw Julia Lawall raised one question. I'm not sure whether it is for this paper or the last paper. Maybe there is a time delay. So her question is, what happens on failure? How does the user detect and react to failures?
I'm sorry, what does one?
I'm I'm not sure whether maybe it is for the last paper.
Hello, it's Claire here from the ASE team. It was for the first paper.
Okay. Maybe there is a time delay. Okay, sorry for that.
No problem.
Okay. I have another question. Is that you discovered that there are 6 new bugs in the system? Are these bugs in the systems that you studied? I saw that you studied 2 systems. One is they are from different versions, right?
They are from different versions. No, so in fact, all the 6 bugs are present in the or were present in the last version we studied on the 5.6. But we also the other bugs that we could have found were in an older version because there were some patches confirming this these bugs. But all the 6 new bugs were in the last version, yes. So that is why we could contact the Linux developers, and they could confirm, and they admitted they approved some patches fixing these errors.
Thank you. Any other question to ask Nick? Okay. So if not, let's thank Nick again and move to the